For billions of years, stars have functioned as the universe's elemental factories. Deep in their cores, intense pressure and heat fuse light atoms into increasingly heavy and complex ones. This fusion engine runs reliably until it hits iron. At this specific point on the periodic table, fusing nuclei no longer releases energy, it absorbs it. Without that outward energy to fight gravity, the star's core collapses, triggering its death. To bypass this energetic wall, the universe uses a different strategy: neutron capture. A nucleus collects neutral particles until it becomes unstable, eventually decaying into a new, heavier element. This sequence of radioactive decay is what creates the heavy materials we find on Earth, including every ounce of gold and platinum. Understanding how neutron capture functions is the only way to account for the existence of over half the known elements. Historically, science only recognized two speeds for this process: the slow S process, which takes thousands of years in red giants, and the rapid R process, occurring in seconds during neutron star collisions. Both the slow and rapid paths leave distinct chemical signatures in the stars that eventually form from their debris. But in the early 2000s, astronomers discovered ancient metal-poor stars on the outskirts of the Milky Way that didn't follow the rules. Their heavy element ratios didn't match the signature of either process. These observations directly contradicted the binary models astrophysicists had relied on for decades. The data suggested that our map of how the universe built its planetary building blocks was missing a major mechanism. Theoretical astrophysicist Falk Herwig began modeling scenarios that could explain these results, such as a born-again white dwarf siphoning mass from a companion and reigniting. The conditions in these models aligned with a forgotten theory from the 1970s called the I process, or intermediate neutron capture. To prove this intermediate path existed, theorists needed to know the exact reaction rates of specific, unstable isotopes that are nearly impossible to find in nature. Since we cannot look inside the core of a dying star, the investigation moved from the telescope to the particle accelerator. By colliding nuclei at immense speeds, physicists can briefly recreate those stellar conditions on Earth, shattering atoms to see how they behave. The testing ground for this cosmic mystery is the Facility for Rare Isotope Beams, or FRIB, in Michigan. Each experiment begins with stable elements like calcium, accelerated to half the speed of light. This beam slams into a beryllium target, fragmenting the calcium into the same rare, unstable isotopes found in stars. A magnetic separator sorts the results, funneling the specific isotopes under investigation into a specialized detector. As these isotopes decay, they release flashes of gamma rays, allowing researchers to record the exact rate at which they capture neutrons. By capturing these elusive decay rates, experimentalists provide the raw data required to simulate the entire I process. When theorists plug these new reaction rates into models, they generate a specific chemical cocktail predicted by the I process. The lab results and telescope observations perfectly match. The elemental ratios in those ancient stars are exactly what the simulation predicted. This direct alignment confirms the I process as a distinct third major pathway for heavy element creation, expanding the recognized map of nuclear astrophysics. With the intermediate process defined, the lab is now preparing to isolate the even rarer isotopes involved in the rapid R process. Recreating these reactions is a cosmic DNA test, allowing us to trace the stellar ancestors of the elements that eventually formed our planet.